Well, hello everybody, it's Dave again, and we're on to lesson 2 in our exploration of significance testing. Now we're going to actually take a look specifically at dealing with a significance test with a population proportion. So if you remember our last lesson, we played around with this free throw shooter who claimed they could shoot 80% of their free throws, but we found, of course, that when we did the simulation, we ended up with a proportion of 0.64, which was much, much lower. And that actually gave us evidence to suggest that the null hypothesis of p being equal to 0.8 was potentially incorrect. So the last lesson, we actually played around with this idea, starting off with very much the same concept here. We're working with the idea of state, plan, do, conclude. And if we look at state, we can see that there's two very important elements to the statement of our significance test. The first thing we see is that the two hypotheses are clearly labeled. You'll remember that H naught is referring to the null hypothesis, meaning that there is no change and that the proportion is exactly what the person claims it to be, which is p is equal to 0.8. But the alternate hypothesis, or the alternative hypothesis, is listed as being less than 0.8 because we're claiming that the individual is actually overestimating their ability to shoot their free throws. So remember that with a significance test, the whole idea is we are making a claim against the statement about the population parameter of interest. Now, we sort of glossed over the next part in the last lesson because we actually simulated this particular scenario. I think everybody would recognize the fact that doing that repeatedly would be really quite challenging, and there's a whole lot more chances of error. So what we do instead is we try to exploit our concept of normal distributions and this idea of the sampling distribution. And so with the sampling distribution, we recognize the fact that there were conditions that were required for us to be able to make statements like the center of a sampling distribution is equivalent to the population parameter, given that the following three conditions are met. In this case, remember, the most important one out of all these, of course, is the idea of randomness. If randomness isn't at play, then you absolutely can't do it. There's too much bias associated. The 10% condition was the condition that we were using just to make sure that the independence of our selections were actually being upheld. Remember that if we sampled too much of the population, we would potentially change the proportions associated with that population, which is a big no-no in statistics. We say all the time that more is better, but in this case, too much is a bad thing because it breaks down our model. And the last thing again is again one of our reasonings behind using a normal distribution, and it's of course the large counts condition. And in this case, n times p and n times 1 minus p both have to be greater than 10. So if we take a look at the sampling distribution here, you'll see that it's obviously centered right on 0.8, which is the first major statement that we make when we start to calculate values associated with this. We are now in the do section of a significance test. And you can see that our notation is pretty clear that the mean of the p-hats, which in this case means the center of the sampling distribution, is supposed to be equivalent to p, which in our particular example is equal to 0.8. The standard deviation of the significance test, however, is going to change a little bit because now we have a sample size. We're talking about 50-shot sample sizes, which means we can't just calculate the usual standard deviation like we would if we had all the population parameters. So instead what we do is we actually will calculate the standard deviation using that sample size as you've seen right there to get an answer of 0.0566. This is an important thing to recognize, is that if it was just the square root of p times 1 minus p, you're calculating sigma all right, but you're calculating it for the population itself. So now we see that we have a center, we have our observation of 0.64, and when we had a simulation in the last lesson, we were able to pretty quickly find the p-value because we would just count the dots. But now we have this nice continuous normal distribution, which means we should be able to use previous understanding of how to calculate this p-value. That really what we want to do is we want to actually show that we understand something about what's going on. So we're going to calculate a test statistic. This is the general case, but we've actually calculated this before in the past by just taking the observation minus the parameter divided by the standard deviation. This is where a big important element for you to remember is this is the standard deviation of the sampling distribution. So we have to make sure that we use that calculated value and not any other type of calculated value. But we do get an answer of negative 2.83, and if you remember this, the beauty of standardization is now we can see that this value is almost 3 standard deviations below the mean, which is, if we think of the empirical rule, quite a far distance away when it comes to the amount of data that could be farther away than that. And so if we take a look at our original distribution, there's our sampling distribution up top. We see the shaded area, and again, you could use normal CDF on your TI calculator with the mean and standard deviation and be just fine, but at the same time, I want you to show understanding, so please make sure that you're actually, first and foremost, standardizing your normal distribution, and then you're finding your p-value that way. But you can see from the examples on the screen there that A and B both give you the same results of a value of 0.0023. Now, those of you that remember from the previous lesson, you'll remember that we had a value of 0.0075, which could suggest that, well, maybe something's different. Well, guess what? We're going to have the same conclusion when we actually have to make our inference at the end anyways. So it really doesn't matter in this case. Again, this is an approximation using a normal distribution. We know that if we had simulated this, we would still end up with the same inference at the end. So we've talked about the state, we talked about the plan. Again, the conditions absolutely have to be met. If any one of the conditions aren't met, I would say still go through with the calculation of your model, but at the end make it abundantly clear that one of your conditions has not been met, therefore we question the validity of our statements. In the do part, a lot of folks focus on the do because this is where the calculations are in, yet from a statistics standpoint, it is probably the least important part. But when you're in the do part, I would definitely recommend calculating your test statistic before you find the p-value. If you're going to use your calculator, make sure you don't do calculator speak, and you make it abundantly clear what your inputs were and what the value came out. So if we summarize this with some basic ideas, we're looking at the 3 conditions that have to be met. These are the conditions that allow us to approximate our sampling distribution as normal with a center equivalent to the population parameter and standard deviation being the equivalent of what you see before you. It's important because what we're going to do next, of course, is calculate the p-value using this normal distribution, whether it be standardized or otherwise. If we take a look at the summary specific to proportions, you can see that if we take an SRS of size n from a large population and we want to test the null hypothesis against some sort of alternate hypothesis, then we are going to standardize this particular normal distribution, and then based upon whether we think it's greater or less or not equal to, we're going to go ahead and perform a one-sided test or a two-sided test. Remember, this two-sided test is interesting because it's basically making a statement that we know it's not right, we just don't know which way it's going to be. When it comes to a two-sided test, there's really not a huge significant difference, with the exception of, because we don't know what side of the distribution it's on, we have to consider both sides. So that means that when we have our test statistic, we have to find the area on the lower tail and the upper tail and add those particular areas up, and that will be the area that we compare to our significance level of whatever alpha might be. So now that we have these statements, we can take another look at confidence intervals, because the interesting thing about confidence intervals is that they tend to give us more information because it's actually giving us a potential value for the population parameter. We're not actually doing that. We're trying to find from a significance test if our observation suggests that the parameter of interest should be different than what it's actually listed as. But the neat part is, and this is an important element to remember for future studies, is the connection between the confidence intervals and the significance test. And the idea of a significance test of either reject or fail to reject can actually be tied to this confidence interval, because let's not forget that when we're creating the confidence interval, we are using a z-score, and from that z-score we're actually going to define the area by which the amount of data in between is established. So in the case of a 95% confidence interval, that means that we have 5% outside, which means that if we're dealing with a two-sided test, we have area on both sides, and if we're comparing it to an alpha level of 0.05, well, that's really the same idea as a confidence interval, which means that we're going to receive similar information about the population parameter. So this is a big element that we're going to want to remember. Of course, we learned from the last lesson that we also have these other types of error that may be associated with our overall conclusions, but that's only in the case of having additional information. So when it comes to these types of errors, there's a very interesting calculation that we can now do. We know that we can't establish a type of error until we have further information about the given scenario. There has to be more work done for us to get a better sense of what the true parameter is. But we do our best with statistics to actually calculate whether we A, can find the parameter of interest given some sort of interval, and B, put that against a bunch of different observations to see if that parameter should perhaps change with the idea of significance tests. Well, the thing about that's interesting is if you really think about what we're doing with a significance test, a type 2 error would be a fail to reject the null hypothesis when it's really false. Well, we already tied this idea to alpha being a type 1 error, which is you reject but you find out that it's true. Well, that means that the entire other end of the distribution is actually the probability of performing a type 2 error where we fail to reject but it's really false. The big thing that we have to recognize is we can actually determine how powerful a significance test is if we start playing around with alternative parameter values given the likelihood of committing a type 2 error to see how many values above that test statistic would still result in the appropriate results. So what do I mean? Well, this is a tricky one. So first we'll define the power. And the power of a test against a specific alternative is the probability that the test will reject the null hypothesis at a chosen significance level when a specified alternative value of the parameter is true. The best way I know how to deal with the power of a test is to actually just work through a problem with you. So let's deal with this idea here. We have a potato chip producer wondering whether the significance test with the given hypotheses based on a random sampling of 500 potatoes has enough power to detect a shipment with 11% blemished potatoes. So the idea again is that we're going to find the value by which we would reject the null hypothesis given our original center. Then we're going to use that test statistic on a new distribution with this alternative center of 11% and find out what the probability would be of rejecting given that case. So the first thing we do is we take a look at our original sampling distribution, and we see that at our alpha level of 0.05 we could find a test statistic to be 0.0999. Now at this point hopefully you don't need to know how to do that. However, we're talking about an inverse norm scenario here. Now we have that test statistic, but what are we going to do? Well, now we're going to figure out if we have a center of 0.11 instead of 0.08, what is the probability now that we would effectively be able to reject that particular shipment? So you can see what we've done here is, I'll go back again so you can see it. We have our original line here right on the test statistic, and now we'll slide in this new distribution, and we can see that the area above that, which was originally the area for rejection, is a much larger area because of course there's more distribution in front of it. However, this is the test statistic that would fail or reject the null hypothesis, which means that the area above it in this distribution is going to give us the power of the test to detect that p is equal to 0.11. So another way of saying it is, since we reject the null at alpha is equal to 0.05 if our sample yield produces a proportion which is our given test statistic, we'd correctly reject the shipment about 75% of the time. So the power of the test isn't a wishy-washy gut feeling sort of scenario where we say, well, we feel pretty good that it would catch it. No, this is actually a multiple step calculation to determine, first and foremost, do you understand that the power of the test relates to this idea of the types of error. And once you have that test statistic, what do you do next given an alternative center? So in this case, our power is about 75%. Please make note of the language associated with this interpretation. So that concludes our lesson about a one proportion z-test and our first specific type of significance test. Again, state, plan, do, conclude is absolutely essential, and your ability to understand how these types of error and this concept of power plays a role in making overall conclusions of our results, whether they're valid, whether we could reject other values if other scenarios came up, and basically really allowing us to make more analysis possible. So next up, we have significance testing with a sample mean. Have a great day.